Thank you for that introduction. As he said, I'm from the National Renewable Energy Lab in the U.S., and I'm going to be talking about valuation of essentially utility-scale energy storage. Some of these ideas could probably be scaled across the spectrum of the power system, but I'm going to mainly focus on production cost models because that's what I have a case study for from the Greening the Grid study. But I also want to talk about how we do this generally at NREL and some other ideas we have. So this is a kind of zoomed out from some of the other talks you've been looking at or hearing this morning. And I think it's an important first cut at understanding whether storage is actually going to add value to the system. Certainly, technologically, there's a lot of promise in storage, but whether there's value there, whether storage can actually get revenue out of the power system is an important thing to consider. So I'm going to talk about two models that we use at NREL. The first being the price taker model. Some of you are probably familiar with these, and the second being production cost models. And I have an example of energy storage in India looking at production cost models. And then I'm going to speculate a little bit about the markets in India, and I'm sure I'll get myself in trouble on those last couple slides. But okay, so looking at these two valuation approaches. So the price taker approach is, I would say, a more simple approach than looking at production cost models. And what we do is we use the marginal value of historical market data and try to understand what value storage could have gained from a revenue perspective if you're a merchant storage plant. And this is slightly complicated in markets that aren't restructured, so this could be a little different than how things look at India in the future. But from a purely market perspective, you can get a lot of information about what a battery could make in a market setting with this price taker approach. And I'm going to spend a little more time in the full system value using production cost models. So these are operational models and trying to understand the operational value to a utility or the value to a society. And you can also get some insight into the market value of batteries with these models. So just to take you simply through the price taker approach. So as I said, this is essentially looking at restructured markets, and you're using historical market data, so historical price data, and assuming that you can dispatch your battery optimally around these prices. And so if you look at the graph in the bottom right for you, you see in the red line we have electricity prices that have been pulled from, let's say, last year, and in the blue is how the battery is operating around these prices. So you can see that above the middle line there, if the battery is operating, it's producing electricity to the system. It's above the zero line, so the blue is above. And if it's absorbing energy from the system, the blue is below. And you can see that follows essentially the prices in the system, and we're optimizing the battery to get maximum revenue. So there's many caveats to this, one of them being that this is in the past, and things might not always look the same in the future. We're using historical prices, historical load patterns, historical everything, the generation mix, and we can't really look forward accurately with how things might change on the market and how things might change in the system. So these can be relatively simple sort of spreadsheet models in Excel, and you can get a lot of interesting information in looking at these. But the big caveat being that you have perfect foresight of prices, and you are optimizing your battery for revenue based on history. So there are a lot of advantages to this. Okay, the historical data is readily available, so that's good. Relatively easy to run, at least compared to what I'm going to talk about in a few minutes. And this is generally accepted in literature that looking back at the history of prices, you can assume that batteries could do somewhat similarly from a revenue perspective by using these historical approaches. But the disadvantages, as I've kind of already gone through, is that we are looking historically. We're also looking at only the marginal unit. So we're ignoring the fact that batteries might actually offset a marginal unit and change the generation dispatch completely and change how much revenue they could get from one of these prices. And this is tough to look forward to planning studies looking forward to changing generation and changing prices on the system. So not great for planning studies. Obviously, there are workarounds. So you could change prices. You could give some imperfect foresight within these models. And you could try to reflect the uncertainty that already exists on the system. You could also look at changes in load, and you could essentially do forecasts from the battery using load-price relationships, forecast what the battery might have done based on yesterday's performance of price and load, and try and optimize your battery based on yesterday's relationship in load and price. But ultimately, these are workarounds, and it is a little bit limited in looking to the future role and value of battery storage. So for production cost model, I'm sure many of you are familiar with this, but what this is it simulates the operations of the power grid, assuming least cost operation. Okay, so security-constrained unit commitment economic dispatch model is another term that I'm sure you've heard. So this is looking at operations within every period of a year is usually what we do at NREL. Sometimes this can be a shorter period if you're only interested in weeks or months. But essentially, we are feeding in the load that needs to be met. We are showing it all the generators that are on the system that could help meet that load, and having various constraints around the way the generation is dispatched, so that it reflects somewhat close to reality on the way the system actually operates, and meeting that with the least cost mix of generators. And this is just an example dispatch, an example of the outputs that we actually get from these models. So this is meeting the blue line load with all the generation that's on the system, and anything that's built into these dispatch stacks, we can understand the different aspects of that, including ramp rates on certain generators, transmission usage. We can also get locational prices, which are difficult, but an interesting output as well. So there's still a couple ways you can use this production cost model. So one is to look at the revenue that an actual battery would get. So what we would do is we would run a production cost model with a battery installed in our system, and we could base the revenue that a battery could get based on the marginal prices and the storage dispatch throughout the year. So pretty simple, and this is just, again, looking at the total operation for whatever period of year, and measuring how well the battery operated and how much money it can make. There's some hybrid versions where you could run a production cost model, get prices out of that model, and then go back to the price taker approach, essentially. So this is a scenario that you might want to go through if you don't actually have access to a very complicated production cost model scenario. You don't want to go through the trouble of learning all these things, but you can still look ahead to the future and understand what price impacts might be happening, how generation dispatch changes in the future. And this is, this can be a good solution, especially from maybe an academic perspective, given that these models take a huge amount of time to run and understand. The difference-based value is actually more of what we look at NREL, and that's simply doing some scenario analysis. So we run a production cost model for a given scenario without storage. We then add storage and run it again, and we look at the difference between those two and understand what is the system-wide value between those two runs. So I'm just going to talk about sort of a simple example that we went through in the Greening the Grid study. So if any of you were at yesterday's talks, my colleague Jacqueline Cochran talked about the Greening the Grid RE integration study, which was something we did with Berkeley and POSCO here in the Ministry of Power. And essentially what we did was we built a production cost model of India to analyze the future 2022 scenario. And that's kind of key point, because these models are very difficult to run and they take a lot of data. But we built this sort of for a different purpose than just looking at storage. Once we had it, we might as well look at storage. So this was a sensitivity on our production cost modeling. And we were trying to, this is a renewable energy centric study, so we are trying to understand how storage could help mitigate challenges associated with RE integration. And we've heard a number of examples of how that could work already today in the short talks. And I think everybody kind of understands intuitively that storage in the long run seems to pair well with renewable energy. But what is the actual value of that, especially looking ahead to this 2022 scenario? And so we wanted to understand that better, if that was something we needed on the system, and what the actual reaction of the rest of the generation is on the system due to this. Another kind of smaller aspect of this is, does storage help us? Is it an effective alternative to coal capacity? And so I'll just leave it at that. And we have kind of a small side note on that. Okay, so just to set the stage a little bit, I don't want to go too much into the results for this because some of you saw this yesterday, but we are looking ahead to 2022. We put 100 gigawatts of solar, 60 wind on the system. We built out our system around that, so the power system was built out based on CEA and CTU projections for load, for generation, for transmission. So all the different pieces and parts of the power system were built out to 2022, and we put a bunch of wind and solar on this as well. And we modeled this for every 15-minute period of the year in 2022. In our storage sensitivity, we kind of took a sledgehammer approach to this. We didn't want to get into a whole storage optimization study. We just wanted to understand, if we put a lot of storage on the system, what is that going to look like? Does that add value? So we added 20 gigawatt hours of storage. And Sir, who was talking about some of the small system in Germany, is probably a little bit shocked at this sort of number. But as I said, we just wanted to put a lot on and see if there's any value, even at very high levels of batteries, not looking at the capital expenditures. We're not really interested in that aspect of it, and didn't analyze whether this paid itself off in value. It was just a matter of looking at the operational value. And so we put this in the 6 states in India where RE is expected to grow the most. So most of the REs in Gujarat, Rajasthan, Maharashtra, Tamil Nadu, Karnataka, and Andhra Pradesh in our model. And if you're around the Indian power system, you know that these are the 6 states that everybody's talking about for RE growth. And so we wanted to see if batteries could add some benefit from an operational perspective in these areas. So these were 75% efficient batteries. And we fixed our dispatch from the day-ahead schedule. Some of that has to do with the fact that it's very hard to model it not just in the day-ahead schedule. And so there might be additional things that we're not looking at in this, but this was kind of a first cut. Does storage add value, at least from an energy perspective? Okay, so we've heard this a number of times this morning, but just to reiterate, so the hypothesis being that in systems with high levels of renewable energy, batteries can absorb RE energy when it isn't needed and discharged during peak demand. So pretty simple. If we waste less RE, we have less fuel usage and less variable costs. So this is just an example that you already saw. This was actually the western region in our 2022 scenario. And you can see that wind and solar during the middle of the day is taking up a lot of the generation. Our coal plants are turning down during that period. And what you see in red, which is above the load line, is curtailment in these periods. So there's a small amount of curtailment overall, but it is happening, and potentially an opportunity for batteries to absorb that RE energy and discharge it during peak times. So just to give another brief overview here. So nationwide, we ended up with 1.6% RE curtailment. That number is potentially a lot higher, especially in the southern region states. But nationwide, it was not an issue. So if you just pay attention to the bar here, on the left, actually, is our high solar and wind scenario. And just to give you an idea of what total generation looks like, mostly coal, a decent amount of hydro, and that blue and the yellow at the bottom represents about 22% of the total generation. On the right, you have the average curtailment in actually both of our no new RE scenario, which if you weren't at yesterday's talk, you can ignore. And in the orange line is our high RE scenario with 100 solar, 60 wind. And you can see that curtailment is mostly happening in the monsoon season in the middle of the day. Okay, so did the batteries reduce the operating costs? So this is a chart of what is happening on the system between our scenario with storage and without storage. So we see that in our dark red line, when we have storage on the system, it operates during peaks, essentially. So it's generating to the grid during the peak. So the dark red line, okay, so this dark red line here, this is where the storage is actually generating, and this pink line here, so the battery load, this is where the storage is charging during the middle of the day. So that makes sense, that it would try and optimize around certain low-cost resources in the middle of the day. If you think back to the dispatch stack, we had a lot of solar and wind on during the middle of the day, as well as a little bit of curtailment. And what the battery is charging on is all of these lines up here. So this represents the other generation on the system during those times. And I'm just going to go down to our non-monsoon period. It's a little clearer. And what you can see is that especially during the non-monsoon period, we only have a little bit of storage here that was able to absorb the curtailed solar, but mostly it is charging on coal during the middle of the day. And what that ended up doing was leading to a pretty negligible effect on overall emissions and also on savings. There's not a lot of difference between the midday prices of coal and the evening prices, although there is a little bit. And due to the battery having only 75% efficiency, it was not able to make up a lot of that. So negligible savings from a 15-minute dispatch time frame. So as far as offsetting peak coal capacity, essentially it does offset coal capacity almost as much as, it does offset coal and gas capacity almost as much as its capacity value, although not all. There is other generation that it's going to displace first, some of the more expensive diesel and CT units on the system. It's going to try and displace those. So from a coal capacity perspective, not a huge amount of value there. We saw that, again, this is 2.5 gigawatts of total battery capacity, and it offset coal by only 1 gigawatt. It offset peak gas by about a half. And so the rest of it was essentially offsetting other units during those times, and also shifting hydro a bit as well. So using a production cost model is a pretty valuable tool for looking at overall value. It can do most things, essentially. You can, there's a lot of levers that you can pull to ask different questions of storage. You can have storage for many different services throughout in the same model if you would like, rather than just looking at a price sticker approach where it's operating to optimize energy. You could look at ancillary services. You could look at storage, even some difficult ancillary service questions, like if storage is charging, can we count that for double the potential ancillary service that it would be providing to the system? Disadvantages is that it's pretty costly, even when it's free, meaning it takes a lot of time to learn and to work with. These are difficult models. They're very data intensive. And so the question you need to ask yourself is essentially, is the value payback to my own time, not in the batteries, is it better than what I'm getting out of the price taker approach, and maybe some workarounds we could use in that model. So certainly, if these models are built, I think it's a valuable step to take in asking big storage questions, but price taker models are also valuable as well. Okay, so this is where I speculate a little bit, and I'll probably get myself in trouble, but looking at the storage potential in India. So what we looked at was energy, and there was kind of a simple approach to looking at what the value of storage could be in India. But in the long run, I would say that it's likely that as RE penetration does go very high, and I'm talking potentially 50, 80%, batteries could probably be used for some sort of arbitrage. The challenge being that if things like how do they get paid for the value they're adding to the system, and that's a question that if they are doing peak shaving and the market is not a totally restructured market, how are they actually going to get paid? Another thing is if batteries end up being valuable for energy ramping, is that something that could be set up in some sort of ancillary services. So maybe this question actually gets moved down to the next bracket. Ancillary services, I think this is also likely. We heard about some examples of where this is already happening. But from a large-scale perspective, and maybe I can zoom out from a commercial perspective, from a large-scale perspective, this market might not be that big. So in our model, we modeled the spinning reserve that needed to be held in India as 10 gigawatts. This is already being covered to some degree by headroom that's in the coal system. And they're already using the unrequisitioned surplus to gather up different headroom that's on the central generating units. So to some degree, the system itself has some essentially latent ancillary services that could be used. So I don't expect that batteries could come on and completely steal that market. As far as regulation reserve, that might be a slightly different question, but for secondary and tertiary, which we're talking about here and which CERC has outlined would be their targets, this market might be relatively small. Firm capacity, I just put unknown. I would say more likely not, at least in the short term, partly because the PLFs of coal plants are relatively low right now in India. As many people know, they're around 60%. So that suggests that there's a pretty adequate planning reserve margin, at least in the short term, and batteries aren't likely to be able to add to that. And I just want to say this is probably not an exhaustive list. And there's probably one that belongs right in this area, which is distribution network batteries, which could be used for niche applications, PV, maybe distribution networks that have a lot of PV has potential to be a market for that as well. Another one is behind the meter. So there's a lot of captive power in India where diesel gens are running and helping provide a reliable grid for commercial and even residential applications. There might be a market for this, but I would say as grid reliability becomes better, I would hope that captive power is kind of removed off of India's grid to some degree. So that's all I have. I just want to acknowledge my colleague Paul Denhoum, who does a lot of the storage work at NREL. And also, if you're wondering about the grid integration study, I'm not sure this got put up yesterday, but we do have a website. It contains all the, actually a number of publications as well as a forthcoming publication that expands on what Jacqueline talked about yesterday. So thank you.